Thank you very much for the nice introduction. I will start presenting the work about a mechanical model for the long-term shear strength predictions. So, this work has been developed at the University of Balearic Islands and with Professor Antonio Marí from the Universitat Politècnica de Catalunya. And it's part of the master thesis of the student Alex Frontera. It is well known, especially in this conference, that steel corrosion causes reduction in reinforcement areas, change in rebar's mechanical properties, bond deterioration between steel and concrete, and due to the volumetric expansion of corrosion products, cracking, as you can see in this nice picture, and spalling. Moreover, stirrups are generally small in diameter or smaller than longitudinal reinforcement, and they present a reduced concrete cover or reducer with respect to the longitudinal reinforcement, so the shear strength is fastly affected by corrosion. Moreover, shear failures are brittle, so it will be necessary to avoid shear failures during entire lifespan of the structure. So the idea of this work was to combine a shear strength model plus a material deterioration model, so to have a long-term evolution of the shear strength. Moreover, we have to take into account that steel corrosion will probably be influenced by climate change because the rising sea level supposes more exposed structures. The rising CO2 concentration will increase the risk of carbonation of concrete, and also the temperature increase influences in more dilatation and thermal contractions, so more damage to the structures, and also an acceleration of chemical processes. Talking about shear strength, it's necessary to mention the existence of mechanical models and experimental models. The empirical models, in general, are only valid in a studied range. So it will be necessary to have broad databases to use empirical model in a generalized way. And very often, different sets of equations will be necessary for slightly different mechanical scenarios, mechanical cases, because it will depend, the equations will depend on the databases. But nowadays there exist sound mechanical models that have already been tested for many different circumstances. In this case, not necessarily new sets of equations are needed for every situation, and the parameters governing behavior and strength appear naturally in the derivation of the mechanical models, allowing their extension to different cases or scenarios. Several years ago, at UPC and UIB, we developed the multi-action shear model, that is a mechanical model that considers the contribution of the stirrups, of the shear reinforcement, VS, you can see it here, but also the concrete contribution through three different concrete actions that will be the shear transfer through the compression zone, here, down crack concrete zone, and the shear stresses transfers through the critical shear crack, we will say this component here, and of course the dowel action of the longitudinal reinforcement. This model was developed for rectangular beams, but was very soon extended to beams with T cross section. The model was simplified, the MASM model was simplified into the Compression Chord Capacity Model that considers that the main contribution of the concrete is through the uncracked concrete in bending, and the other shear transfer actions are implicitly, not explicitly, considered. This model has been validated up to date with around 3,500 empirical tests for reinforced concrete and prestressed concrete beams with and without shear reinforcement, with rectangular or T cross section for slender and not slender beams in case of fatigue, steel fiber reinforced concrete, beams with internal FRP bars, with external chain memory alloys, in different many situations. So we thought that it was necessary to extend the model for the case of corrosion. As commented, we consider that the main shear transfer action is the shear transfer through the compressed zone, and this is an approach that many researchers have during the last decade adopted. In fact, 5 years ago, it was an international call of models to help in the update of the ACI 318 code, and 6 different models were presented to this procedure, and they were published or summarized in a special issue of Concrete International. And you can see in the left, 2 models consider the shear friction as the main transfer action, but the other 4 models from South Korea, 2 from the United States, and our model from Spain consider the compression zone as the main resisting action. All these models were at the end more or less considered in the ACI 318-19 shear update. I'm not going to fully enter into the model, the compression chord capacity model, but at the end you have a concrete contribution plus a steel contribution. The steel contribution is from a classic truss model, and the concrete contribution considers a size effect. Here, this term comes from fractures mechanics and was developed by Professor Bazan, and the relative neutral axis depth, that is a little bit, let's say, the key of the model. Just this year, we presented the extension of this model for corrosion-damaged reinforced concrete beam. It's openly published here in this journal, and we try to keep it as simple as possible. So we only consider 3 influences of the corrosion. For the shear reinforcement, we only consider the remaining area of the stirrups after the corrosion. The same for the longitudinal reinforcement. For the longitudinal reinforcement, to consider the remaining area after loss due to corrosion will influence the neutral axis depth. That of the stirrups will influence, of course, the stirrups contribution, and also the corrosion product expansion may produce cracks, as I previously commented, and cause concrete spalling. In this situation, in this scenario, we will have to reduce the concrete width of the web, and we consider this when the average cross ratio loss of the stirrups is over 10%, and we use this model previously published. Just in some scenarios with huge deterioration, it's necessary to consider the reduction of the compression zone due to the spalling in the compression zone. Well, we use a database with 146 tests, and you can see here with these black rhombuses that if we do not adapt the model to consider the corrosion, we will go to unsafe results, especially unsafe for heavily corroded beams. But the red triangles here show you the correlation of the empirical shear strength and the predicted strength considered the corrosion. In fact, for these beams, the mean value was 1.19 with a coefficient of variation lower than 20%. These values are completely similar to those reports for our model with many other databases. So we think that this is a simplification, but a simplification that works reasonably well for the shear topic, because we have some dispersion in the results in the shear problem that we cannot never avoid it. Well, the model was also studied that for different experimental campaigns relates especially well. And then we are going to combine this model with a carbonation model. And in this case, we are going to use the carbonation model included in the new Spanish structural code that was published just a few months ago. In this code, we have a model that has an initiation time that depends on the Fick's law. In fact, it follows the Fick law, and we'll have a carbonation coefficient that takes into account the environment, for example, concrete sheltered from the rain, then drain air in the concrete, and the use of Portland cement or additions, fly ash, or silica fume. And then the model also presents the loss of diameter of the Ribas due to corrosion with corrosion rates that will depend on the exposure class, as you can see here, with exposure classes from Eurocode, in this case for carbonation, and here for chlorides. I'm not going to comment here the case of chlorides. We are working on that nowadays, but you can see that, of course, the corrosion rate is much higher. Well, here you can see what we are now able to do, that is to have for a beam with a geometry, to have the original shear strength, and then to study after the initiation time, and then when carbonation corrosion starts affecting the stirrups, then we have also the initiation time for the longitudinal reinforcement. And you can see here that the shear strength degrades, especially when we take into account the stirrups. We also are considering the longitudinal Ribas corrosion, but the influence is of course lower. And here, for instance, you can have a beam that you were thinking in a exposure class, but it was wrong. And then we can, for a already built beam, we can consider different corrosion rates. You can see here 2 micrometers year or 4 micrometers years. And in this case, at 60 years, the model is predicting the cover spalling. And after this, you can see this dashed line, of course, the degradation will be higher because the corrosion rate will increase. We are not considering still this scenario. We get until here. Well, so the diagram is quite simple. You have the original shear strength, then you calculate the initiation time for the carbonation in this case. If you want to evaluate the shear strength for a time that is not higher than the initiation time, then you go to the original shear strength. But on the other situation, then you have to reduce the steel section of the stirrups and also the amount of longitudinal steel that is collaborating. If the reduction of the cross section of the stirrups is lower than 10%, then you can calculate with the original web width or the web width of the concrete flange. But if it's higher, then you will have a reduction in the width, and you can also obtain the strength here. So just to finish and to conclude, the joint application of the Compression Chord Capacity Model and the carbonation model has been presented here in this conference for the first time, allowing the prediction of the long-term evolution of the shear strength. More research will be carried out, including the realization of parametric studies and the combination of the Compression Chord Capacity Model with a chloride-induced deterioration model. This methodology, we think, could help taking decisions both in design and in structural assessment. And with this, I finish my presentation. I hope you have enjoyed it, and of course, I'm open to any questions. Thank you very much for your attention.